Let's talk slow version. Meet the microbes that could eat your thrush. At this very moment, almost everything around you is being eaten. Invisible to naked eye, organisms called microbes swarm every surface. Hordes of bacteria, archaea, and fungi has evolved to produce powerful enzymes that break down tough organic material into digestible nutrients. But there's one particularly widespread type of materials that almost no microbes can biodegrade: plastics. To make most plastics, molecules from oil, gas, and coal are refined and turned into long, repeating chains called polymers. This process often requires temperatures above 100 degrees Celsius, incredibly high pressure, and various chemical modifications. The resulting man-made polymers are quite different from the polymers found in nature, and since they've only been around since the 1950s, most microbes haven't had time to evolve enzymes to digest them. Making matters even more difficult, breaking most plastics' chemical bonds requires high temperatures comparable to those used to create them, and such heat is deadly to most microbes. This means that most plastics never biologically degrades, they just turn into countless tiny, indigestible pieces. And pieces from most common plastics like polyethylene, polypropylene, and polyester terephthalate have been piling up for decades. Each year, humanity produces roughly 400 million more tons of plastic, 80% of which is discarded as trash. Of that plastic waste, only 10% is recycled, 60% get incinerated or goes into landfills, and 30% leaks out into environment, where it will pollute natural ecosystems for centuries. An estimated 10 million tons of plastic waste end up in the ocean each year, mostly in the form of microplastic fragments that pollute the food chains. Fortunately, there are microbes that may be able to take a bite out of this growing problem. In 2016, a team of Japanese researchers sampling sludge at a plastic bottle recycling plant discovered Ideomeles sequences 201F6. This never before identified bacterium contains two enzymes capable of slowly breaking down PET polymers at relatively low temperatures. Researchers isolated the genes coding for these plastic digesting enzymes, allowing other bioengineers to combine and improve the pair, creating super enzymes that could break down PET up to 6 times faster. Even with this boost, these lab-grown enzymes still took weeks to degrade a thin film of PET, and they operate best at temperatures below 40 degrees Celsius. However, another group of scientists in Japan has been researching bacterial enzymes adapted to high temperature environments like compost piles. And with one particularly warm pile of rotting leaves and branches, they found gene sequences for powerful degrading enzymes known as leaf branch compost cuttings. Using fast-growing microorganisms, other researchers were able to genetically engineer a high quantity of these enzymes. They then enhanced and selected special variants of the cuttings that could degrade PET plastic in environments reaching 70 degrees Celsius, a high temperature that could weaken PET polymers and make them digestible. With the help of these and other tiny diehards, the future of PET recycling looks promising. But PET is just one type of plastic. We still need ways to biologically degrade all of the other types, including abundant PEs and PPs, which only began breaking down at temperatures well above 130 degrees Celsius. Researchers don't currently know about any microbes or enzymes tough enough to tolerate such temperatures. So for now, the main way we deal with these plastics is through energy-intensive physical and chemical process. Today, only a small fraction of plastic waste can be biologically degraded by microbes. Researchers are looking for more heat-tolerant plastic boards in a plant's most hostile environment and engineering better plastic enzymes in the lab. But we can't rely solely on these tiny helpers to clean up our enormous mess. We need to completely rethink our relationship with plastics, make better use of existing plastics, and stop producing more of the same. And we urgently need to design more environmentally friendly type of polymers that our growing entourage of plastic boards can easily break down.